Bismillahirrahmanirrahim. Let's start this lecture about this section 4.4, and it is about congruences. In previous lectures, we saw the basic form of the congruence into the form of A, A congruent to B, mod M, like that. But here we have now the definition for the linear congruences, and just wait, I am just finding the pen. Okay. Yeah. Now it's okay. So linear congruence between two integers a and b would be in this form, and here a, b are integers. M is a positive integer as you have before, and then this x is a variable. This is something extra in the equation that you have from your previous slides. So if you have that x here, then this form and this equation is known for the linear congruence. And there is a related theorem for that one, which is the theorem 1. Its first two lines are its statement. And this theorem is saying that if you have the A and the M, where A is a integer and M is the M is the integer number for the modulus, and this is the situation, and then we can call them that these two are, if they are the relatively prime. What is the meaning of relatively prime? It means that their GCD is equal to 1. And this M through which you are dividing and getting the remainder, this would be greater than 1. Okay, so this is the situation that if you have A and M, and if they are relatively prime, then an inverse for this A modulo M must exist. Then an inverse of A modulo M will exist, you can say. So this is the statement of theorem 1. You have to keep it in your mind. So some question like that, A modulo M can be or will be given to you in the upcoming slides, and it would be asked that what is the inverse for that thing. And this is, if this is the situation, then how you can, so that solution, whatever the inverse, we can call that inverse a solution for that problem. So that solution would be a unique solution. Okay, that would be a unique modulo M. Now, for example, look at this example 11. And this is saying find an inverse of 101 modulo 4620. So now we have, this is, you can recognize this form. This is the form A modulo M, like that. And you have to find the inverse. And now you can solve this problem. So first, you have to see that either they are relatively prime. And for relatively prime, what you have to judge? You have to judge that their GCD would be equal to 1. If it is the case, then they are relatively prime. And how you can find that GCD? You can find the GCD with the previous latest technique, which is about which is the Euclidean algorithm. So you can use the Euclidean algorithm and then you can find the GCD of 101, comma 4620. So that is the first step to solve this question. And then the second step is you can use the Bezout coefficients. And how you can find the Bezout coefficient, it is discussed in the previous lecture. If you have two integers a and b, then this, if this is the left hand side, this would be equal to this right hand side. And here a, b are the number, and this s and t are the extra integers that you will get here, like here. This 4 and 5 are the for this s and t, and these are a and b, according to previous lecture. So now then you have to use the Bezout coefficients to you have to find those. And for example, here you have these two numbers, a and m. You can consider this m as a b. So then what? With a you will 101 a plus 4620 b is equal to 1. So first, again, the first step is the Euclidean algorithm that you will use to show that the GCD of these two numbers is 1. And then it will be sure that they are relatively prime. The next step is to find the Bezout coefficients. And for finding the Bezout coefficient, this is the equation. So you have to convert your given information, which is one number is 101, other is 4620. So that would be, so you have to check that 101 multiplied with some a or 4620 multiplied with b, that should be equal to 1. This is according to the previous definition. Or you can say that these are the two numbers 101 and 460. So these, anyhow, and these are the s and t that you have to find. Anyhow, let's start. So these are the two steps. First is Euclidean algorithm, and then you have to apply the Bezout coefficients step to find these related coefficients. And only then, for example, when you are finding the Bezout coefficients, you know that this 4620 is the value for the m, and this 101 is the value for the a. So finally, whatever the value that you will find, whatever the integer that you will find with this 101, like that, with, for example, this is the number a and this is the value for the s. So suppose that this 101 is a. So whatever the value you will find for with this a, that would be your inverse. Now, first step, use the Euclidean algorithm to check that the GCD of these two numbers is 1. So for finding GCD through Euclidean algorithm, what you can do, you can keep the big number on the right hand side, or you can divide the bigger number with the smaller number, bigger integer with a smaller integer. So that's why we are going to write 4620 equal to, and here we are dividing it with 101. When 101 will be multiplied with this 45, you will get some number. When you divide that number with this 4620, you will get this remainder. So you can divide it with your traditional method, and then you will see that this would be equal to that thing. That is first step by using the Euclidean algorithm. Then what? According to the Euclidean algorithm, then you have this, you have to take that value, which is now your x, before this step, which is now your x, and this is your remainder, which is y, and then you have to divide x with y. For example, in this beginning step, this 4620 is your x and this 10y is your y. But in the next step, this number from which you were dividing, that would become your x. You have to write it on the right hand side, equal to, and this 75 will become your y. You have to divide this 101 with this 75, and 75 multiply multiplied by with 1, and after subtracting from 101 you will get 26 as a remainder. So now this second step is complete, and you have to go on until your y will become 0. And here y is 75, here y is 26, which is the remainder also. And in the next step, now this is your x and this 26 is your y. So we are dividing 75 with 26 multiplied by 2, and this is your remainder after subtracting this value from this 75. Now this is my x and this is now my y according to the Euclidean algorithm. I'm not explaining Euclidean algorithm because it is explained in the previous lecture. So the students who don't know what is Euclidean algorithm, they can go to that lecture and come back again here on this example 11. So now 26, and similarly divide it with 23, and this 3 is the remainder. Now what is next? This is my x23 and this 3 is my remainder. So that's why I'm writing 23 is equal to and divide it with this 3. And when this 3 multiplied with this 7, it is 21. And 23 minus 21, I have 2 remainder. And now this 3 is my x and this 2 is y. So 3 is equal to, when 3 is divided by 2, this 1 is the remainder. Now this 2 is my x and this is my y. So I should have to continue this process until the y will become 0. So here y is not 0, so I have to go on. This is my x now. So that is why 2 is equal to, and this is my divisor, 1 multiplied by 2, 2 minus 2. Now my remainder is 0, which is not mentioned here. And according to that Euclidean algorithm, when y not equal to 0, so this loop continues until y not equal to 0. So leave it. So that's why I am just executing that algorithm over this one. And here, then what? Here, what is the last non-zero remainder you got here? In this last step, when y is 0, your Euclidean algorithm will be stopped when y is equal to 0. And at that time, and when y will become 0, and at that time, remainder is updated in this y. And 2 divided by 1, whatever it is, so then you will have 0, and then it will, when it is y not equal to 0, then continue. If it is 0, break it. So this last step is the something extra step for the last terminating condition. So this is the condition which was last preserved, which was preserving the values of x and y. And here the remainder is 1. So go into that statement, and here 1 is the remainder. And that remainder is basically your GCD according to that Euclidean algorithm. So that's why we are saying that the GCD of these two numbers 101 and 4620 is 1. And as the GCD is 1, so one thing is clear for this question, that they are relatively prime. So that is proved. Now we have to find the Bezout coefficients. When we will find the Bezout coefficients for these two numbers, those would be some additional number. One will come here in as a combination with this 101. other will come here as a combination with 4620. And this 4620, according to the given thing, it is a modulo value. So then you have, and so then you have to move to the other number, that is the A. And whatever the coefficients that you will find with this 10A, that would be the inverse of this question. And we can find these coefficients only, we can find these coefficients by using this Bezout method. Now moving next to the slide for these Bezout methods. So how can we find the Bezout coefficients? We can find the Bezout coefficients by reversing these Euclidean steps. The steps that you have done here, you have to reverse those steps. So from where you have to start? From the second last step. Here, this one. This is the last one where y is equal to 0. So that's why you have to ignore it. And you have to take that second last step where the remainder is not 0. And here the remainder is 1 and not 0. So what is this one? This is 3 is equal to 1.2 plus 1. So you have to start from here. And how you can start it? Move this 1.2 or 1.2 to the left hand side, and it will become 3 minus 1.2 equal to 1. It would become like that. And it is what written here. It is what written here. 1 is equal to 3 minus 1.2. So this is your starting point. And then what? So we are starting with this thing that 1 is equal to this left hand side is equal to that right hand side, and on the right hand side we have 3 minus 1 over 2. And now you have to put values for this 3 or 1.2, whatever fits. And from where you can get these values? From the next step. And this is the next step now. And from this step, you can do what? You can move this 7.3 to the left hand side, and it will become 23 minus 7.3 is equal to 2. So you have the value for the 2. 2 is equal to 23 minus 7.3. So what you can do now you have, if you have that value from that equation, that you can put those values in place of these 2. And that's why 3 minus 1 dot, and we are putting those values 23 minus 7.3 from this part. Move this 7.3 and it would be equation for this 2, and then put those values for 2 here. Okay, now simplify it. How you can simplify it? So this is 3, but it is 7 times. And this is 3, not mentioned, but it is 1 time. And this is 1 minus 2, 3. So, okay, rewrite it. Minus 1.23 according to that multiplication, dot multiplication, that is portion. And then this 7, this minus plus, okay, and then 7 and plus 1, 8. And it will become 8.3. Okay. Now it is simplified. Now we will search. We will go for the next step. And what is that step? We have to find something from here. So if you can move 1.23 to the left hand side, and then you will have 26 minus 1.23 is equal to 3. Now you can replace the value of 3 here. And we have 3 here, so you can replace the value here. So similarly, again, minus 1.23 plus 8 dot, and place the value of 26 minus 1.23. You are replacing that value from here. Okay. And similarly, you can go on with this one, with that one, and finally with that one. So, and similarly, you are just putting this value and then simplifying. Okay. And then again, you are putting the value for 23, and the value of 23 you will get from here. You can see 23 is equal to from here. And then you will get the value for 26, and similarly for 75. And here we are putting the value for 23 and simplifying. And then we are putting the value for 26. And here we are putting and then simplifying. And then we are putting the value for 75, like that. And finally, we are simplifying it. We have 101 45 times, and we have 101 26 times. And this minus and minus will become plus 45 plus 26. It will become whatever, you have to multiply it. It will become 26 plus 45, it will become 1601 times what value? 101. And similarly, this is minus 35.426, which is that one. Now, this 101 is the number that you have here in the question. And this 4620 is the number which is the M in your question. And you know that this is the M, so you don't need this coefficient which is given with this M. So what coefficient you need? This one, 1604, because it is with the A. So this 1601 is the inverse of 101 modulo 4620, which was the question. Find an inverse of this one. And I hope that you now have the complete understanding. Now, moving next. Yeah, I'm just checking that the recording is going on or not. Alhamdulillah, it's going on. So now moving next to another important topic, that is again about congruences, but now you are moving towards complexities. Anyhow, here on this slide, we mentioned something about Sun Tzu puzzle. This is a Chinese name, and this person asked some questions which are mentioned here. He said in the public, he said that there are certain things whose number is unknown. You can imagine that he was saying in the scholarly people. And he was saying that there are certain things in the world whose number is not known or unknown. And when you will divide that number by 3, you will get 2 as a remainder. And when you will divide that number by 5, you will get 3 as a remainder. And when you will divide that number with 7, you will get 2 as a remainder. So, and then he posed a question at the end that what is that unknown number? So basically he posed a puzzle among those people or before those people. So if that is the situation, we can convert this whole story into a form of a question, because this is something he's talking about congruences. He's talking about congruences. For example, how you can convert this whole story into the form of congruences. For example, here he said that number is not known, which is x, and when you divide that number with 3, you will get 2 as a remainder. So this is x congruent to 2 mod 3. This is that statement which he has given here. And similarly, he said that the number is not known. When you divide that number with 5, you will have 3 as a remainder. So this is the form of congruence, x congruent to 3 mod 5. And similarly for the last statement. So this is what he's talking about. He's talking about congruences in a simple form. So this is the puzzle. So now you have to find that unknown number. So we will inshallah solve this Sun Tzu puzzle later. But before that, we have to see a theorem, because this theorem will help you to solve that Sun Tzu puzzle. And this theorem is called Chinese remainder theorem. And in this theorem, the statement of the theorem is this, that you have some positive integers which are mentioned by m1, m2, and mn. So these are the positive integers, but these are pairwise relatively prime. What it means, pairwise relatively prime, just for the recap, because we already have seen the definition of pairwise relatively prime. So pairwise relative prime is that if that series is given to you, you have to make their pairs. For example, m1 with m2, m1 with m3, m1 with m4. So you are making pairs, and then you have to check that their GCD is 1. If the GCD of those pairs is 1, then they are called pairwise relatively prime. That was the definition. And these are the positive, relatively prime positive integers, greater than 1. Also greater than 1, because mostly we will use these m1, m2, and mn as a moduli. We will use them to divide some number. So that's why the number through which you are dividing some number should not be 0. So that is greater than 1. And if it is 1, then you don't have any effect. Anyhow, and there are this is the statement of the theorem. And there are some other numbers, a1, a2, and so on, an, which are the arbitrary integers. Which are what? Which are simply arbitrary integers. And if you will write these numbers into the form of a congruences, then you have x congruent to a1 mod m. So this is also the statement of the theorem. Okay, we have not started the proof yet. We have not started the solution or the proof for this theorem yet. So this is the statement of the theorem. So we have x congruent to a1 mod m. So now you can understand that these are the m1, m2, and so on, m1, which were mentioned here. And these are the a1, a2, and so on, an. These are the arbitrary numbers, but here these numbers are the remainders. When you divide this x with m1, this a1 is the remainder. When you divide this x with m2, you have this remainder. And similarly, you have this remainder. So, but this x is 1 at all the lines. It is not something different at each line. No, this is only one number. That number, when you will divide with this m1, you will get this remainder. When you will divide this with m2, you will get this one. And this Chinese remainder theorem saying that this congruences has a unique solution for the modulo m. How this is basically your first step when you will solve some problems or some questions after this theorem. So this problem will have a unique solution. That solution is X actually. That solution is X. But for the modulo M, and this modulo M you can calculate by multiplying all these moduli from M1 to Mn. So you have to multiply all moduli with each other, and then you will get some resultant value. That is the resultant value for the modulo M. And keep it in your mind that that would be the first step if some question will be given to you as an exercise, like here. Okay. Now, these statements are the additional statement for your understanding. So that has a unique solution. That solution would be X. This X we have to find, because I already told you that this X is same in all the lines. It is a unique in all the lines. Anyhow, so that unique solution would be X, and that X would be greater than or equal to 0 and less than M. Also, this is additional information. So that would be unique. And if you have some other solutions, those would be congruent modulo M to this solution. We are saying that it is a unique solution, but there are some opposite solution can exist, and if it is the case, then those would be congruent modulo M to this solution X. Anyhow, if you don't understand, leave these statements. But these statements, you have to keep it in your mind. And here a proof is given, and I divided this proof into 3 steps and numbered with 1, 2, and 3. I have given them numbers so that you can keep these steps 1, 2, and 3 in your mind. Actually, these 1, 2, and 3 are the steps which you will need to solve a problem like that. For example, we will see in example 12. So if you will forget these things you will forget these things, but don't forget these 1, 2, 3 like things. That's why I have mentioned, I have labeled it with numbers. So for the proof of this theorem 2, Chinese remainder theorem, if these are the congruences given to us, what is the solution for that? We have to find a solution for the X, and that would be the answer. That would be the answer for that theorem. So we have to find a solution, that the solution is existing, and that solution would be unique solution. Okay. Now, what is the first step? Here, the first step that you have to do here, and also keep it in your mind, and if in future some question will be given to you to find the solution for X, and some equations will be given to you, then how you can do that is you can do, or you can solve those questions with these 3 steps. And this is the step 1. What you have to do, you have to, after multiplying all moduli, you have to keep the result in M, and then what? You have to divide that M with each moduli. First, you have to divide that M with M1, and then you will get a value for the capital M1. Okay, and then you have to divide the same M again with M2, and then you will get the value for the capital M2, and so on. You will have to divide the value of M with Mk, and you will have the value for capital Mk. So this is the step you have to do. I I explained this step. For example, this is the m. First you have to calculate the m, and then you have to divide that m with each moduli. And then you will have the values into the form of capital M1, capital M2, capital M3, and so on. So this is the step that you have to do. Okay, now step number 2. And this is also the step. And if you have, this is also the proof. Not the this step number 1 is not only the proof, this is the starting point. And this MK is the product of modulize this MK. I know that. I will give you that understanding with the evidence. Maybe you will not understand that, but when I was explaining the example, at that time I will give you the understanding. But keep this thing is in mind that you have to divide that. And you will get M1, M2, capital M1, capital M2, capital M3, and so on. Now, what is the step 2? According to the theorem 1, what is theorem 1? Theorem 1 is this one. When A and M is relatively prime, there is an inverse. Okay. So now step 2 is that you have to find the inverse. What is the step 2 of this Chinese remainder theorem? You have to find the inverse of mk modulo m. In this previous step, you are getting values for m1, m2, m3, m4 up to mn. I can say you are getting the value for mk. Okay, you are getting the value for mk. So now I can say, if I can say mk modulo m, you have both of these values. You have the value for m1 and small m1, capital M2 and small m2. You have these values from this previous step. So in this step 2, you have to find the inverse of all these capital mk modulo small mk. And you can change the value of this k from 1 to n. Then you have these numbers for each moduli if you are solving a question. But for the theorem, this is only one is needed. And this is the form, previously for which you have calculated the inverse here in this example 11. So now you have to calculate the inverse for that thing. This is step 2. You can find that inverse by using that method, previous method. But in theorem, we are saying that this is according to the theorem 1. If you will go into that theorem 1, okay, where is that one? Okay. Anyhow, so you have to, for example, you have these things and you can convert, or you can say those things also like that, mk, yk congruent to 1 mod mk. This is the step number 2 of this theorem. Whatever the equations you will have there, you can, this mk is available here. This small mk is also available here. Okay, that one and that one. This y is something, yk is something extra. You have to convert, you have to convert, or you have to form you are given things into this form mk yk congruent to 1 modulo mk, and when it will be this yk that you will have here would be the inverse. That is one way to find a inverse from this form, and the other form is that you can use this procedure. First this one and then that one. But this was an example, and you know that you can find the inverse. You can find the inverse. And here in the theorem, we are generally just saying that if you will have this form, then for these inputs, then this yk would be the inverse. So this is the second step that you have to do in this theorem. Just keep that step in your mind because it will help you to calculate the final answer for your congruences. Okay, after the step 2, now you can understand that now you have the values for capital M1 and for example y1, similarly capital M2 and y2, capital M3 and y3, for all these cases from A1 to AN. So then the next step, you have to sum them up. You have to sum them so that it will give you the value for the x. And here you can find this is the equation where it is mentioned that x is equal to, here m1 y1 is that form, m2 y2, mn yn is that form, or you can say that you have the value for the m1 and you have the value for the y1 which is inverse m2 y2, and here m2 is that mk or that mk, and here y1 y2 is you will get from here. When you will have the inverses for all the cases here in step 2, then you can write those inverse values here for all the y's. And this A1, A2, and AN are your remainders. This one, A1, A2. You don't have to calculate. This would be already available in your question or in your problem. So you have to just multiply them here. And then you have to sum up their values. And then you will get some number. You will get some number here. Final resultant number, because after the summation you will get some value here for the x. That value for the x, if you have some value like that, you can convert that value again into that form. So x, for example, here x congruent to ak, mk, yk, which you can write like that. This ak is the remainder, as we know, and then mod mk. You have to write the remainder and you have to write the moduli for this simple congruence. And this is the x. And this is not needed to mention. So then you have to, this is the third step. First, you have to sum it up. You will get some number. You have to convert that number into this congruence form again. And that would be your final answer for that x. Okay, so this, anyhow, from this Chinese remainder theorem, so here in the proof of this one, we have we have started here that we will multiply all these moduli and it will give us the result. It will give us the result m. Then we have to multiply that m with all the moduli one by one, and we have to keep the values in mk. And that mk, now we have to find the inverses for all the mk's, but we can transform our mk for all the moduli, mk modulo mk, which you can write into the form of a congruences. And when you will write here, you will need some variable yk, that would be the inverse, and in this step 2 you will have that inverse. When you will have that inverse, then you are able to sum them all, and you can sum it up, and then you will have some final number for that x. By the way, you have the solution here now, but you have to convert that solution into the congruence form, because we started with the congruences. And when you have that congruence form, that would be your final solution. This is the proof. And here k for all 1, 2, and also an n. This is the general proof, which you can see from this, which you can verify from this example 12. So here, according to the steps of CRT, CRT means Chinese remainder theorem, this theorem which we discussed here. Okay. Just a minute. Yes. Example 12. What is example 12? Example 12 is the same example 4, which is given here, yeah, because now we are going to solve this Sun Tzu puzzle. This is basically example 4 in the textbook. So we are going to solve. So these are the congruences which will be given to you: x congruent to 2 mod 3x, congruent to 3 mod 5x, congruent to 2 mod 7. It would be like that. It would be like that. These will be given to you. So now in this example 12, you have those 3 equations with you. And what is the first step there? First, you have to multiply all the moduli, and then you will get the small m. What is the first step? So these are the moduli: 3, 5. This is m1, this is m2, and this is m3. So you have to multiply this 3, 5, and 7 with each other. And what you will get? 3 multiplied by 5, 15, and then multiplied by 7, maybe 105. So multiply all these 3, 5, 7, and then you will have the value for the m. And that is 105. This is according to this step. This was the step which is mentioned here in the Chinese remainder theorem. And then what? And then now we are dividing this 105, which is m, with the first value, with 3. And we are getting 105 divided by 3, we are getting 35, which is m1. And similarly, we are dividing 105 again with this second moduli, which is m2, and we are getting 21 and capital M2. Similarly, 105 with this 7 and m divided by 7, you will have 15, which is m3. And this is step number 1 of the Chinese. So this is here, you can see m divided by k for k is equal to 1, 2, and so on, and you are getting mk. And you are getting mk. And here it is written mk. This mk is the product of moduli. Moduli is what? M1, M2, M3. These are all moduli. Mk is the product of moduli except for mk. Except for mk. Mk is not included, and the remaining moduli are included, the meaning of that one. So if, for example, here, if you will look for M1, except this MK, except this one, it is the product of the other moduli. 5 multiplied by 7, you have 35, and this 3 is not included, which is, for example, here it is the case of 3. So that small mk, this 3 is not included, but for others, it is the product. That's why it is 35. And for the next one, and here you can see 5, that 5 is not included, and rest are 3 and 7, 21. And similarly for that 7, this 7 is not included, and this 3 and 5, 15. So that statement is saying that mk is the product of the moduli except for mk. And now you understood that this mi is the moduli's, and this mk is something specific, maybe for that one. And so that's why mi and mk have no common factors greater than 1. So they don't have any common divisors or common factors greater than 1 when I is not equal to k. When I is not equal to k, you can apply on the same thing. On the same things, you can apply this statement also. This is the other meaning for that. The other meaning for this product of moduli except mk is that one. It's the same thing. When you don't have any factors, then it follows that GCD of that mk, small mk and capital Mk is 1. Okay, when you don't have any factor greater than 1. So it means that 1 is the only factor. Anyhow, coming back here. So this is step number 1 that you have done here. According to the Chinese remainder theorem, we are going to find the solution for the x. And what is the next step? Next step is to find the inverses for example, this m1, for m2, for m3. And how you can write it? This one, m1, this is the, for example, the remainder. M1 is equal to 35 modulo 3. This is what you can write. This is what you can write. This mk modulo, what are the values for small m1 in this question? For the small m1, this is the value 3, which is also mentioned here. And what is the value for this mk, capital M1? Capital M1, you calculated capital M1, the value 35 for this capital M1, which is mentioned here. So capital Mk modulo small mk for M1 is 35 modulo 3. So you are writing these things from previous information, nothing new. And if you have this one, you can write it into this form: 35.yk congruent to 1 more 3, which means that divide that right hand side with this 3 and get 1 as a remainder. And you can use any value here in place of this yk. And if this whole equation of congruences holds, then you will have the value for here. For example, if you will give yk a 0, if you will give 0, then you don't have anything for the division with 3. But if you will have 1, then 35.1, 35, when you will divide it with 3, what you will get? 11 multiplied by 33, you will have 33. When you will divide or subtract it with 35, you will have, what is the remainder? 2, and it is 1. So this is not. So keeping it 1 is not okay here in this equation. So then what? Keep 2 here. When you will put a 2 for the yk, then it will become 35.2, it will become 70 after multiplication. Now divide that 70 with this 3. And what is the remainder now? If you will divide 70 with 3, for 70, okay, 3 2s and then 3 2s. So when you multiply 3 with 21, then you will have, what value you will have? 63, okay. When you will divide that 3 with 23, then you will have 3 3s are 9 and 3 2 is 69. So you will have 69 and 1 would be remainder. And so what I want to say, when you will keep the value of this yk 2, then it will become 70, and after dividing that 70 with this 3, you will have 1 as the remainder. You can divide it and you will have these values. You can verify these values. So here 2 is a right value, and then that 2 is basically the inverse of that m1, which is 35 modulo 3. So find these inverses for this m1, for this m2, and for m3. So 2 is the inverse for that one, and similarly for 1, m2 is equal to this 21 modulo 5, by using the same concept as I discussed here for m1, and then write it in this equation form. 21.yk is equal to 1 mod 5. We have started with 1. When you will keep 1 here, 21. When you will divide it with 5 for the 20, and then you will have 1 as the remainder. So okay, so this equation holds for value of 1 here, and that one is now the inverse for m2, and similarly 1 is the inverse for m3. So now you have in this step 2, now you have found the inverses for the m1, for the m2, and for the m3. And what is the next step? Next step is to write it into that summation form and calculate their sum. This is the third step. So now I have only 3 equations, so I can write that into this form: x congruent to a1 m1 y1 plus a2 m2 y2 plus a2 m3 y3, according to, that is the formula, by using that thing. And okay, what is a1, a2, and a3? a1, a2, a3. What is the question? This is the a1. This is a1 2. This is a2. This is a3. Which are the remainders? 2, 3, and 2. Okay. This is 2, 3, and 2 are the remainders for the a1. m2, you have the values for here. m1, m2, and m3. 35, 21, and 15. 35, 21, and 15. And these are the inverses. 2 is the inverse that you have found here. And similarly 1 is the inverse here, and similarly the final one is the inverse here. Now multiply and sum up, and then you will get 2 to 33 as the final integer. Now convert that integer which you have here into a congruence form, when you can write into a congruence form. How you can do that? Divide that 23 with this M105. Okay, so to divide that 223 with 105. When you will divide, you will get 23 as a remainder. So you can write 233 congruent to 23 mod 105. This is the conversion into that form. How you can convert? By dividing it with this M, not M1, not all moduli, the resultant moduli. Divide that one. Okay, when you have that form, then this is the remainder. Then this is the remainder. Now, this 23 is the smallest positive integer. When you divide that 23 with 3, you will get this 2 remainder. When you will divide this 23 with 5, you will get 3 remainder. When you will divide this with 7, you will get 2. This is the question which was asked before. And you have the solution now. This 23 is the solution. This was the question. When divided by 3, you will have this 2 remainder. When divided by 5, you will have this 3 remainder. When divided by 7, you will have this 2 remainder. So now you can see, after this last congruent form, you have to check that remainder. This 23 is that positive integer. When you will divide it with 3, you will have this remainder. Divide by 5, you will have this remainder. And 7, you will have this remainder. So this is the solution now. So this is the solution now. And now, okay, now these are just general topics for the large integers. So it is just representing that how you can perform, how the computer perform arithmetic on large integers. So this concept is also using the previous concepts. So suppose that if you have M1, M2, and so on, Mn, which are the moduli, but they are pairwise relatively prime moduli, then you have to do what? You have to multiply them all, and then you have the M as their product. And then what? Then by Chinese remainder theorem. So we are just revising the previous concepts, but a little bit difference will come. So by the Chinese remainder theorem now, you can also see the exercise 28. Exercise 28, which is given in the exercise section, okay? So by the Chinese remainder theorem, we can find an integer, we can display an integer a, and that a would be greater than or equal to 0 and less than m. What is that m? This is the product. This is the product, okay? Not these m1, m2, m3s. So we, by Chinese remainder theorem, then we will have some integer, and this is the condition for that integer, and that integer can be uniquely represented by n tuples. Because we are using n, so that's why we are still using the n. So that integer that we will have by Chinese theorem, we can represent that integer with n tuples, and those tuples will consist the remainders. after and will consist the remainder after division by modulize. These are the modulize m1, m2, and so on, mn, and so on, mn. So this is and so for example, you can divide that integer with m1 and then you will have some value here. You can divide that integer which you are getting with m2 and then you will have some value here, and so on. You can divide that integer with mn and you will have some that value here. So this we are calling it n tuple. So for that, so by we will use Chinese theorem, and that theorem will give us an integer, and that integer can be represented into that tuple n tuple, and that tuple consists what, when you divide it with m1, so we are using mod, so that will consist remainders. So that will consist, this tuple will consist remainders, and these tuples you can use further for further things. Anyhow, now there is an example to understand these things, and in this example uh, we uh, we have to prove computer arithmetic with large integers. Okay, and uh, so we will take some example, and here in this example we will take the example of adding two numbers, and that addition is a arithmetic operation. Similarly, you can perform the multiplication, division, and subtraction and other operations, arithmetic operations. Uh, so if you have less than 100, if you have integers less than 100, and if you want to add them, then their addition would be much quicker, much faster on a single machine, on one machine as compared to other machine. And if the arithmetic operation is with large integer, for example, you have operation with less than 100, if you have integers less than 100, and if you have large integers, then you can understand. And if you have to perform the arithmetic operation, then you can understand, then the arithmetic operation with small integers would be much faster than these large integers. So that is something. So that's why, so that is the idea which is giving us this idea, which is giving us this strength that we can use the moduli. And for example, here we are taking moduli less than 100, so starting it with 99, 98, 97, and 95. So these are, we are considering from 100 to backward, only we are considering only 4. It can be more, but just for example, we are considering more. And they are relatively prime. So these are the modulize. And for modulize, we are saying pairwise relative prime modulize. So that's why, anyhow, so 99, 98, 97 and 95. So if you will make them pairs, and then you will have their GCD1. And when they are relatively prime, it means that there is no any common factor between their pairs greater than 1. 1 is possible or not. So now we are going to, so here we have a supposition that small numbers evaluates much faster as compared to large integers. That is something comes into our mind that it is a fact, but we have to prove that. So that's why we are saying that if it is we are saying that it is a fact. So now we are going to transform. So that's why this idea gives strength to this dimension that you have to convert your large, you have to transform your large integers into small integers, and then you have to do the arithmetic. So that is basically the thing. So in this example, in the first step, we are uh, supposing two numbers, and then we are summing up their tuples, which is the n tuple, and then finally we are converting into congruences to get a solution for the addition of two numbers. So these are the steps. So anyhow, uh, this example is saying that suppose some numbers for addition, and this addition is the arithmetic operation. So anyhow, by Chinese remainder theorem, now we have supposed some modulize from 99 to 95. So what you have to do, you have to multiply these modulize. And when you will multiply, you will get this large integer first. We have not supposed the two numbers yet, which we want to add, but we have just introduced that these are, after multiplying the modulize, we have this large integer. So now this large integer, so now you can use integers less than this for performing arithmetic operations on them. And this is the limit that we are getting from after the multiplication of these modulize. Anyhow, this is the large integer m, which we are getting after multiplying this m1 with m2 with m3 and m4. Now you have to do what? You can represent this large integer. You can represent this large integer with its remainders after dividing it with the modulize. But suppose we can take, according to this fact, we can take any integer less than this value. So that's why we are taking this number randomly, 1, 2, 3, 6, 84. And this number randomly. So these are the two numbers. And then what? 1, 2, 3, 6, 84. You can divide this number with 91, and then you can represent it with, this is the remainder. You can divide this number with 98, and this is the remainder. You can divide this number with 97, and this is the remainder. You can divide this number with 95, and this is the remainder. So now this is the way how you can represent your large integer into the form of a tuple, which consists of remainders. So this is you have done for this large integer. Similarly, you can do the same thing for this number by using these modulize, and you have this second tuple for your second number. So this is the step one. Now you have supposed two numbers. And now what? In the next step, you have to add these two tuples. And how you can do that? Just look over here. This is the first tuple plus this is the second tuple. Add this 33 with this 32 because it is related with 99. Add this 8 with 92 because they are related. Add this 9 with 42. Add this 91 with 16, and you will get this value. 33, 32, 65. Similarly, 8 and 92, you will have 100, and you will have the values like that. And this mod 99, you are just writing it again because you know that the first is 99, second is 98, 97, 95. So we are just writing 99, 98, 97, 95. We are we have not performed the division yet, but we are just writing here in this step. And now 65 is less than 99, so this would be the remainder as it is. 100 is less than 98, so what is the remainder now? Because it will give us remainder. 100 when divided by 98, you will have this remainder too. Similarly, 51 is less than, so 51 is the same. 105 is greater than this 95, divide it, and what is the remainder? 10. So now you have this tuple, final tuple, which is containing the, which is consisting of only the remainders. And what is the final step? Now, because you want to add those, you want the result for the addition of these two numbers, you have converted them into tuples, you want to add them. This is the result for the tuples, but this is not giving you an idea that what is the result for addition of these two numbers. How you can get it? Convert it into the congruence, and then you can get it. Convert it into the form of congruence to get the final sum. So these are what? These are the remainder. You have all the information. So 65, for example, here 65 and mod is 99. 2 and mod is 99 from the previous information, from this information. Similar. So this is the congruence forms. And now you know that how you can calculate these congruences by using this previous approach. By using this previous approach, then you will have that number here. That will give you that result. That will give you that result. So you can apply the same procedure, or you can do the exercise 53, and then you will have that number. By the way, for this question, you can just add them. You can also add them 6, 4, you can verify them 0, 8 and 5, 13 and 1, 14. So you can verify like that. But actually, your computer will do what? Your computer will calculate like that, as you have done here. And then you will have like 23 here. So you have to do the same thing like that. And then you will have that number. And that number would be the additive solution or the addition solution for these two numbers finally you will have. Okay. So this congruence, this last point is mentioned that this congruence is not needed. You have the tuple on here. But if you want to get the integer like 5, 30, 1, 40, then you need that congruence from this tuple. Then you need that third step. Otherwise, it is not needed. Okay. Now, the last Fermat's little theorem. With this theorem, if there is a number p which is prime, and this is the equation by the way, a raised power p minus 1 congruent to 1 mod p, and here p, this one or that one, if that p is prime, if that p is prime, then a is an integer not divisible p, then this a would be an integer that would be not divisible or dividable by this p. So you can use. So what is the example for that? For example, here, find, I'm just moving fast because I don't have much time and I have to go somewhere for the exam. So find 7 222 mod 11. So we have to find that one. So you can solve this thing by using that equation. By using that equation, what you have to do, This equation is giving you an idea that you have a prime number like that. After mod, you have the p. After mod, I have the p. This is 11 is a prime number. So then what? So this 7 is now my a, and this p minus 1. But so 11 minus 1 is 10, and but this is triple two. So then what? You can find it, but this is a huge number, so it's not easy for me to find what is that integer. So then what? You can use this little theorems format to find their solution quickly. How you can do that? By using this theorems format, you know that this is 11, which is p. So mod 11, you can write it into that theorem form. Then it would be 7 raised power 11 minus 1 is 10. 11 minus 1 is 10. Congruent to 1, we are writing according to that equation. 7 raised power 10 congruent to 1 mod 11. So after subtracting 1, this is the p, but this is p minus 1 according to that one. So 11 minus 1 is 10. So this is written according to this theorem. But this is not a solution yet, because it is not equal to triple two. We have to make it according to that triple two. So now we are saying that whatever the power of this 7 raised power 10, for example, 7 raised power 10, whatever the power, we are saying it is a k. It would be congruent to 1 mod 11. So how much power you can increase it here? 50, 100, whatever. Because it is that one, so always it will divide that time, and you will have again the remainder 1 here. That is not an issue. So that is again according to that theorem. But we have formed this equation by using that Fermat's little theorem. After that, what we can do now, we have to convert it into that. We need this something. We need some value above this 7 equal to this triple two. So how you can do that? We can divide this triple two by 10. And how you can make it equal? So triple two is equal to, when you divide 10 with 22, you will have 220. And then plus 2, 220 plus 2, it would become triple two. So this is something you have to, these are something, the factors and the remainders that can be equal to this triple two. And then now you can rewrite your 7 triple two like that, because 10 is something that you have found here. And then by using that 10, you have found something else with some remainder. And then now you can rewrite your 7 triple two into this form. So here 7 raised power that 10 multiplied by that 22. So I have 220 here, and plus 2 I have 7 triple two. Okay, this is equal to that one. Okay, now I can write it. So 7 raised power 10 and then again raised power 22. So if power has a power, then that we have the multiplication here. So we have the multiplication here, and we have converted that notation into that notation. And then this remainder 2, which is the power for that 7, is written here separately. 7 raised power 2. So this is 220, and this is dot 7 raised power 2. And now I am finished with this one, but now we are going on that right hand side. With this one, we are finished. So with this 7 raised power 10, we have added this 22 power 22, and then this 2. So you have to add it also here to make this congruence equal. So that's why this one we have added, it was just 1. So that's why we are writing 1 time 22 times. Also on on this side. When this is 7 raised power 10 is only one time. Make it 22 times. So, okay, also for 7 raised power 10, it is only one time. Also make it 22 times. Okay, that is fine. And 7 raised power 2 is, okay, I'm just opening it up and it is equal to 49. Okay, write it like that. And then congruent, okay, 7 raised power 10, and this is completed, and then mod 11. Okay, mod 11. This congruent to 122.49. Here I am using the congruent notation. And you can write after it mod 11, but okay, it is just, we are just calculating. So now what? This is 1 and this is 49. 49 multiplied with 1, we have 49. When you divide this 49 with 11, so what you will get? 11 multiplied by 4, 44, and 5 would be the remainder. So that you can further write it as congruent to 5 mod n. The question is find what you will get when you divide this integer with this modulus 11. What would be the remainder? So now 5 would be the remainder, and that is the answer. Okay, Jazakallah, and these are the exercise questions that you have to you solve for this section 4.4, and see you again in the next class, inshallah.